In this video, we are going to determine the potential of a charged rod with direct integration. I'm also going to revisit the electric field integration that we've done with the same problem, but I want to show you the similarities here. So let's start out with something you know. Let's have a rod of length 2L. Why 2L? Well, then my limits of integration will be minus L to L instead of minus L over 2 to L over 2, which I find quite obnoxious. So just call it 2L, no big deal. Of course, there's some dq here, and I'm looking for the electric field and then the potential at this point, which is above the midpoint of the rod. I'm going to call this distance y. In previous examples, we've called it a. It is a constant with respect to x, but I'm going to let it stay y because what we're going to see is that if I let it stay as y, even though it's constant with respect to x, I can let this range up and down as long as I don't move in the x direction. If I let this point range up and down, I can come up with a general expression for the field, not just a particular expression for the field. So on this rod, I put some charge q. Then, of course, I have lambda as q over 2L. I need this because this is always my strategy. I use lambda to turn the differential charge element into a differential length element. I can express dq as the charge density lambda times dx, right? That allows me to integrate over the rod. This is all stuff we've done before. I'm just reminding you of it. So here we are. To then form the differential field at this point, I say dE is equal to dq over r squared. And then I'm going to recognize that because this is symmetrically over the midpoint, any electric field at this point will have a component in the horizontal direction that will cancel with a component from a symmetrically placed charge, right? So over here, there's another dq there. The horizontal component of the field due to this charge will look like that. The horizontal field due to this charge will look like that, right? And they're going to cancel. So the only one that contributes is the field, in this case, in the y direction, in the up and down direction. So I can go ahead and peel off that component. Let me put a theta right there. And that means the vertical component is going to be a function of the adjacent side. That's the cosine of theta. And I get the cosine as y over r. So when I integrate both sides, I'm going to get E is equal to K. I don't have enough room there. Let me go to the next line. E is equal to K. Instead of writing dq, I'm going to write lambda dx, and then I have a y. And then instead of writing r cubed, I'm going to write what r is, which is x squared plus y squared square root. X squared plus y squared. And then when I cube that, I get to the 3/2 power. And that's my expression. Okay, clean it up a little bit, pull out the constants. This is going to be k lambda. Now remember, y looks like a variable, but I'm integrating over x, and I'm not changing my x. I'm always looking over the midpoint here. So y can come out of the integral because it has nothing to do with x. And that just leaves me with the integral from negative L to L, right? That's why I chose 2L, of dx over, and you can't see that, dx over x squared plus y squared to the 3/2 power. So this integral is what I'm going to be evaluating. Again, feel free to explicitly evaluate that integral if you want to, or feel free to look it up on a table if you want to. When I do that, get this back in frame, I get that the electric field at that point, after I evaluate this integral, k lambda y times x over y squared, x squared plus y squared square root. That should be an x. I started to write something else and then I fixed it and it looks bad with a Sharpie. I'll fix it in the next step. Okay, and this is of course evaluated at negative L to L. Okay, well I've got a y, so the first power here, y squared here. I'm going to lose one of these guys. So let me clean that up and evaluate. So the electric field is equal to k lambda. And then plugging in L at the top, I get L over y. I'm just left with one y times x squared plus y squared. Sorry, that should be L squared. See, I said I'd clean it up and I messed it up again. Minus negative L over y, L squared plus y squared square root. Alright, so putting all that together, I get 2k lambda L. Alright, 2 because I've got a minus negative. And then that is times, that's going to be over y, L squared plus y squared square root. Okay. Now, remember, in this integral, y was a constant, but within this form, as long as I stay true to my original condition of being over the midpoint, I can actually let y range up and down. That's the advantage of keeping this in y. So can you call it something like a to show that it's a constant point? Yes, you can. But you can also let it range up and down just by keeping this a variable. Of course, you have to remember that it can only be over the midpoint because those were the conditions of integration, right? That's where we got these limits. So that's the magnitude of the electric field. If I want the vector nature, I have to recognize that the field above the rod is going to be pointed up, and so I can just easily slap on a j hat to get that field. Okay? So this is something that we have seen before. A few chapters ago, we did similar things to get the electric field. So hopefully this is all ringing some bells. My contention is to get the potential will not be really any different. So let me put this here so we can see the graphics still. To get the potential at that point, I use the same idea. I have dq here, which I'm going to express as ultimately some lambda dx. But then I just write down the differential form of the potential. This is not a differential volume now. This is the potential. So this is at this point, due to the contribution of one of these dq's, gets me k dq over r. Just that simple. No r squared. I don't have a cosine of theta coming in because this is not a vector. There's not a component to throw away. I just have dv there, right? Let me integrate both sides. Make a substitution in for dq and for r. I'm going to get v is equal to k lambda integral from negative L to L of dx over x squared plus y squared square root. I'm going to be a little bit clever here and recognize that this is a symmetric function. All right, I'm sorry. I'm going to recognize that this is an even function evaluated over symmetric limits. So to make my evaluation a little simpler, let me just evaluate half of the integral from 0 to L and multiply the rest of it by 2. If that's sorcery to you, feel free to evaluate the whole thing. Not going to change anything, but your calculus teachers will get there. That's the best I can say. Symmetric function over even function over symmetric limits means you just evaluate half the integral and multiply it by 2. So I'm going to have that dx over square root x squared plus y squared that evaluates as, let me move this over, that is going to evaluate as log x plus x squared plus y squared square root. Make sure you can still see that. You cannot. This integral evaluates as the log, sorry, I need the 2k lambda there. And the integral evaluates as log x plus quantity root x squared plus y squared. And of course, this will be evaluated from 0 to L. All right, so let me scoot that back over and evaluate. Let me rewrite it so it's in frame. 2k lambda log x plus x squared plus y squared square root, evaluated from 0 to L. At the upper limit, that's pretty simple. I get log of L plus square root L squared plus y squared. Remember, x was my integration variable, so I'm plugging in L for x, not y. At the lower limit, what am I gonna get? It's gonna be minus log, can we see that? Keep running out of room. Minus log, well, if I plug in 0 for all the x's, I get 0 plus square root of 0 plus y squared. So I just end up with the square root of y squared. I get the log of y. Like that. And then I'm going to apply rules for logarithms and rewrite this way. 2k lambda log L plus L squared plus y squared square root over y. And that is the potential of the charged rod at that point above its midpoint. Again, I'm going to leave this in terms of y, so this can now vary as I move up or down. As long as I stay above the midpoint, this works. And so I've gotten the electric field by direct integration. I've gotten the electric potential by direct integration. So my encouragement would be to start from scratch on both of these. I guess scratch would be right here. And evaluate this and see if you get what I got. I wouldn't say follow step by step. Evaluate the integral and then go back and see if you got what I got. If you didn't, go back and try to fill in some gaps. Do it for the electric field and then do it for the electric potential, right? When you're confident with that, then we will do another process to get the field and the potential a different way.